talk about directed graphs in general. Okay, and some connectivity kind of properties in directed graphs. Okay, so directed graphs, what is in directed graphs, what is the analog of connected component? So this connected component is in undirected graphs, and we want to see in directed graphs is there an analog, correct? So what is a connected component? So you can so take any vertex S, and you can reach any vertex from S, correct? Then so if from S you can reach a vertex V, you say that they lie in the same connected component, correct? But it's easy to see that this simplistic extension does not work out. Why? Because it might be that, so it does not split the graph into equivalence classes. What could happen is, for example, consider this thing, V1, V2, V3, something, correct? Let's say even V4, V4 to S is an edge. So now you can see that we can reach from, and let's add some more. So let's say S prime can reach V3, and S prime can reach V4. Okay, so there's some directed graph. Here you see that you see that you can reach from S to V1, and but you cannot reach from V1 to S, correct? So now it's not, so you will not be able to partition the vertices into equivalence classes. Do you see my point? So if you say the relation that says that look at for every vertex V, consider the reachable set of V is equal to W, such that V can reach W, correct? Then this is not an equivalence class. These are not equivalence classes, because, for example, V1 belongs to R of S, but S does not belong to R of V1, correct? Am I making sense?
Yes, sir.
Okay, but now look at let's say V2. So so V2 belongs to R of S, because S can reach V2, and S belongs to R of V2, because V2 can reach S via this path, correct? So this induces us, and this kind of looks like so if you look at graph, this part you can think of as one equivalence class, because each vertex can reach every other vertex here. So let's say S of V, let's decide, let's define S of V as those vertices W, such that there's a path from V to W and there's a path from W to V, correct? So our guess is that this S of V is an equivalence class. These S of V's are equivalence classes. This relation that so the S of V's are all disjoint or the same thing. meaning for all v and v prime, either S of v intersection S of v prime is equal to empty set, or SV is equal to SV prime. Correct? Which is how equivalence classes should behave. So there is some relation under which these form equivalence classes. Correct? The S of v's. And this equivalent, this relation we call so strong connectivity. So strongly connected components. So let me define strongly connected components. So let me first define strong connectivity. Or how do I define it? Let's say U and strongly connected. So U comma V are strongly connected if U can reach V and V can reach U. This is notation for can reach via a path, a directed path. Correct? So UV are strongly connected if U can reach V and V can reach U. And now you take the maximal strongly connected, you take so you take the maximal strongly connected components. So when do we say something is strongly connected? When for all U comma V in this set S, U can reach V and V can reach U. So each pairwise, everything in S is strongly connected. So this is a strongly connected component or SCC. And we will actually refer to a maximal SCC. That is, so if you take two vertices out of an SCC, they of course form an SCC also, because both of them are connected. But you want the maximal SCC. You cannot add a vertex to this set to the SCC without disturbing strong connectivity. Correct? Am I making sense?
Yes, sir.
Okay. So maximal SCC is maximal strongly connected component. Correct? Now, so it's easy to see that these are precisely the maximal strongly connected components. You can convince yourself about that because so the collection SV claim is that SV such that V belongs to V is the collection of maximal SCCs. Okay. And why is that? Because firstly, each SV is strongly connected and it is maximal. Correct? So why is each SV strongly connected? Because by definition, so how would you prove that? So take any V and W, sorry, take some XY, X comma Y belonging to SV. And now what does this mean? That there is a path from V to X and there's a path from X to V. And also there's a path from V to Y and there's a path from Y to V. Now putting together, so now we want to prove that there is a path from x to y and path from y to x. Now how do you do that? You take this path and concatenate it with this. You will get a walk, not necessarily a path, but nevertheless every walk contains a path. So you would get a way to go from x to y and similarly from y to x, combining these two. Correct? Means that SV is a strongly connected component. Why is it maximal? Because suppose it's not maximal, you could add an element A to A union SV is suppose a strongly connected component is a SCC also. Then you can easily see that there is a path from V to A and A to V, which means that A belongs to SV. Correct? Do you agree, or is there any problem?
Sir, I did not get the last point, sir. Why is it
Okay,
maximal?
it's maximal because suppose A union SV is an SCC also. It's not max, so it's not maximal, which means that you can add a vertex A to it, and still it would remain an SCC. Correct? So A union SV is an SCC. Suppose for some A. Correct? Correct?
Yes, sir.
So if it is an SCC, we know that V belongs to SV, and from the definition of mm, um, strongly connected component, we know that there is a path from V to A and A to V. Correct? Because this is an SCC, there is a path from V to A and A to V, which means that A belongs to SV already.
Oh, okay, sir.
Correct?
Yeah.
So therefore this contradicts that A was not in SV. So it's a maximal. And now these maximal things naturally partition the and of course if SV is not equal to SV prime, implies SV intersection SV prime equal to empty. Why is that?
Because they are equivalence classes.
Because they are equivalence classes. We have not explicitly proved that, but this is one way to. Yeah. So why are they equivalence classes? Because firstly, V belongs to SV. Then if U belongs to SV, then means that no. So what do we have to prove for equivalence class? That if the equivalence class needs a relation, and the relation is uh, V is related to W if W belongs to SV. Correct? This is suppose our relation. Correct? Now, if W belongs to SV and belongs to SW, implies that um, which is the same thing as saying that V is this thing to W and W is this into X. So which is the same thing. Now we have to prove that V is related to X, but what does this mean? So I'm writing in the wrong order, but this one means that there is a path from V to W and from W to V, and this means that there is a path from X to W and W to X, and now again there's V to X and W and X to V, correct? Which means that X belongs to SV. So correct? So there, this is transitive, and also no, what is it? And also we can prove that it is symmetric. So we can prove that if V belongs to SW, implies that W belongs to SV, if and only if, because this is same thing as V goes to W and W goes to V, W goes to V, and this is the same thing as W goes to V and V goes to W, and these things are equivalent, correct? So I have not done a methodical job of writing it out, but I presume you can do that, correct? So it's in, so this relation is in equivalence class, and now, like somebody pointed out, it partitions the set into these maximal, into these equivalence classes, which are the maximal strongly connected components. Okay, having said that, uh, uh, now let us look at how the strongly connected components, the maximal strongly connected components, uh, so contract. So what are the maximal? Suppose the maximal strongly connected components are S1, SV1, SVK, correct?
Sir,
Tell me.
could you scroll up for a minute? I just want to see.
Sorry?
No, could you scroll up for 1 minute?
Yeah, tell me.
No, sir, a little low. I just want to see the last line. Yeah, one second.
Okay.
Yeah.
So, okay. So, if you have these maximal strongly connected components, you have these maximal strongly connected components, and now you want to draw a graph with nodes which are these components. So you say you put an arrow from SVI to SVJ.
So, excuse me, sir. The
Hmm.
last point which you made, the two strongly connected components, if they have uh, even one common vertex, it means they are the same, right?
Yes.
Thank you.
Yes. So I argued it via the equivalence class thing, that if something, if this relation is reflexive and transitive, then it partitions the universe into strongly connected components, and these strongly connected components are merely these SVs, correct?
Yes, sir. I understood the point. And
Huh.
it will form these equivalence classes and they'll be disjoint with each other.
And they'll be disjoint from each other, as is true for any equivalence. I mean, yeah, for equivalence classes are always disjoint from each other, correct?
Yes, sir.
Another way to see it, like you say directly, is that suppose two equivalence classes have a vertex in common. Suppose these two SCC have a vertex in common. Then you can reach any vertex from here to here and vice versa. And you can reach any vertex from here to here and vice versa. And therefore, from here to here, you can go from here to here, or you can come back from here to here. So these are basically the same strongly connected component, correct? Maximal strongly connected component, correct? Okay. So now, so is that clear? That is what you were saying, na?
Yes, sir, it's clear, sir.
Okay. So now we start to build a graph from these strongly connected components. So what is the graph? We put an edge from SVI to SV. If SVI is not equal to SVJ, so basically, okay, let's say SVI is not equal to SVJ, and there exists W. There exists WI, WJ such that Wi belongs to SVI and Wj belongs to SVJ and Wj belongs to E. So basically, there's a very bad way of saying this Vi, this component, there's an SVJ here, and there's an edge from here to here. Correct? From some vertex here to some vertex here. Correct? Then you put an edge from Vi, from SVI to SVJ. Correct? Am I making sense?
Yes, sir.
So now, what is the graph that you will get? SVK and so on. So you will get some graph, correct? Can this graph contain a cycle? Let's call this graph D. I claim this graph D is a DAG. So
Sir, otherwise
what
they
is
won't
this
be
DAG? What
equal.
is this D? Huh. So V of D is equal to SVI. Let me define it formally. Vi belongs to V of G, and E of D is defined by SVI, SVJ, such that this thing holds true.
So if there is a cycle, then the strongly connected components won't be disjoint.
If there is a cycle, then the strongly connected components will not be disjoint. Yes. So they will lie in the same strongly connected component, essentially. Correct? That's what we are saying. So suppose there is a cycle in D that SV1 goes to SV2, goes to something, 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 SVK and comes back. These are not the same V1, V2, VK. These are some strong, or call it I1, I2, IK, IR, correct? There is a cycle. Then you can go from a vertex from here to here and a vertex from here to here. And inside these, you can go any which way. So finally, there's a way to go from take any SV. Basically, all this entire thing falls in one strongly connected. Correct? So they will not lie in distinct strongly connected components, but that was assumption that SVI is not equal to SVJ. Correct? So this, therefore, this D is a DAG. Correct? Because it doesn't contain any directed cycles. Okay. Now, so basically what we are saying is we have kind of split an arbitrary directed graph into a DAG of strongly connected components. And this is a very nice decomposition. In many ways, you will see later on. So now, how would you determine? How would you construct this DAG efficiently? So you have this one strongly connected component that goes to another strongly connected component. I'm drawing it downwards, but it could be in any direction. It needn't be planar, something, correct? The only thing is there are no cycles in this, correct? So now how would you determine what are the strongly connected components and what is the DAG? How would you determine those? Tell me. So let's say I gave you a vertex. Okay. So this is a DAG. Every DAG has a sink vertex, correct? Do you agree? For example, this is a sink vertex. This is a sink strongly connected component from which there is no edge out. These are source. These are source. This is a source. This is a sink. Now, if I gave you a vertex in a sink strongly connected component, could you determine the vertices of the strongly connected component under the promise that it belongs to a sink? Can you determine the vertices of the strongly connected?
Yes, they would just be all its neighbors, right?
Uh, all its neighbors, meaning this sink contains many vertices which
Like
form a,
if we choose any vertex in the sink.
if we choose any vertex in the sink. Yes, good. Yeah. Now we just look at the vertices reachable from V is what you're saying.
Yes, sorry, not neighbors. Yes.
So you look at the reachable vertices from V, okay, is equal to W such that V can reach W. And because it's a sink component, you cannot go out of the component. So this is equal to S of V. If V belongs to a sink component, RV equal to SV, correct? And finding RV is easy because you just take a box and look at everything reachable from it by BFS or DFS, what, correct? So suppose I gave you a sink component. Now you will mark all the vertices in R of V. And now what you will be left with is a DAG again, correct? If you move this, you will be left with a DAG, correct? Of which this is a new sink component and this is a new sink component, correct? These are no outgoing. The only outgoing neighbors of these were in the original sink components, correct? So now how would you proceed? Now if somebody magically gave you some component vertex here, vertex here, then you would do the same thing for these, remove this, and so on, correct? So does this remind you of some algorithm that we have done? Tell me.
Breadth first.
Not really.
Okay.
Something else.
The topological sort, the
Topological sort, exactly. So topological sort on a DAG, correct? So topological sort is always on a DAG. So you want to do topological sort on a DAG, correct? You want to take, so in a DAG, we started from a source component and we eliminated it. And then we looked at the sources formed there and we eliminated them and so on and so forth, correct? Here we are starting from a sink component, we are eliminating that. Then we are looking at sink components, eliminating those and so on, correct? So there are two parts to the problem. First is identifying a vertex in a sink component and then eliminating those, correct? So how would you find a vertex in a sink component? What is the naivest way you will do it?
Sir.
Tell me.
So what do you mean by sink component? Is it a vertex or like a set of what?
So it is a component, meaning it's a strongly connected, a maximal strongly connected component.
Okay.
It is one of the things that we have these S of V's, correct?
Yes, sir. Yeah.
And we want to identify a V such that it is equal to some S of V, correct? So what is the naivest algorithm that you can think of?
We can take the longest path from any vertex. the endpoint which will lie in sync.
That is not a naive algorithm. I want naive algorithm.
Okay.
So I'm saying you can, for example, check. You can compute R of V for every vertex. R of V is just what I wrote here, correct? This. And I can also compute this R minus of V, which is just those W's, sorry, uh, which can reach V. W such that W can reach V, correct? Do you agree? I can call this R plus, this I can call this R minus, something, correct? And if, so we know that R plus of V intersection R minus of V S of V, correct? Do you agree? Because
Yes.
what is R plus of, that's just the definition of S of V. Those vertices which are reachable from V and can reach V, correct? And so this is one fact we know. And now if you have, hello? Can you see my screen?
Yes, sir.
No, sorry. Sorry. So, so if you know that RV plus is equal to RV minus, I claim this is means that V belongs to a sync component. Meaning everything that can, no, is that correct?
It shouldn't be. Because there will be vertices and other components which also.
No, this is not wrong. Sorry, I made a mistake. So, so what is the criterion for what is the criterion for V to be in a sync component? That RV plus is equal to S of V. So RV plus is equal to RV plus intersection RV minus. Correct? Which essentially means that RV plus is contained in RV minus, correct? So that is a naive way to determine such a V. You compute RV plus, RV minus, and check whether RV plus is contained in RV minus, correct? Is this correct? Is this criterion correct?
Yes, sir.
So, so now how do we convert it into an algorithm? That we will see next time. But it basically, it is an efficient way of doing this computation. It just checks, it just uses DFS and topological sort. It combines them, correct? So, yeah, so think about this and we meet next Tuesday when we will finish this part.
Sir,
Tell me.
so could you explain this last two lines there?
So what I'm saying is, if V is a sync component, RV plus is SV, correct? If V belongs to a sync component, if and only if RV plus is SV. Take a sync component, correct? So is this by implication, both ways implication clear?
Yeah.
we just saw that SV is RV plus intersection RV minus.
Okay, okay.
So I've just written this criterion as this. And now this is the same thing as this. Correct? So, okay. So then we meet next time and we will discuss this. Correct?
Sir,
with the-
Tell me.
Sorry, go on.
No, tell me.
So the last two lines, like they are not equivalent, right? RV plus inside RV minus is not equivalent to the other thing.
It's not, is it? If
It's
RV
not.
plus
They're not equivalent, but the first line implies the second, I think.
Yeah, but don't we need equivalence?
no, but
Wait, they
no,
are.
it's equivalent.
why
Yeah,
aren't
They
they
are.
equivalent?
yeah.
They are equivalent. For Venn diagrams, I mean, you can draw a Venn diagram, correct?
Okay, I'll check.
Sir, in the quiz, there was a question regarding finding the odd cycles. Can you
Huh.
explain it, sir?
So you can find an odd cycle. You need to do bipartiteness, which you can do via BFS. There's an odd cycle if and only if the graph is non-bipartite.
Okay,
Is
sir.
that-
Yeah. If it's non-bipartite, then there'll be an odd cycle. Okay.
There's an odd cycle, and this you can check using a BFS. Whether there's an edge between the same layer. So you will do this BFS layering, correct? And if there are two vertices which have the same distance from the source, and there's an edge between them, then there's an odd cycle. Otherwise, there's no odd cycle. Am I making sense?
Sir, I did not understand.
Okay. Let's see if you have an odd cycle, correct? Let's say if you have an odd cycle, something like, and for simplicity, let's say your source lies on one of the vertices of the odd cycle, correct? So you have an odd cycle, let's say a 5 cycle. If you do, we can remove this restriction, but suppose you start BFS from one of the vertices of the odd cycle, then you will see that these two vertices, which are at the same distance, two each, have an edge between them, correct?
Okay.
Am I making sense?
Yeah. So should we find the distance from the vertex and then?
Yeah. So in
Yeah.
BFS, you can find distances of vertices. And then if there is an edge between two vertices of the same distance, you know that there's an odd cycle. Conversely, if there's an odd cycle, and even if it's so
We don't need the distances themselves, right, sir?
you just need parity of the distances.
Yes.
Yes. So yeah, that was that. Maybe it was a bit hard question, but bit of a hard question, but yeah, it was.
So someone said like there is a DFS algorithm as well.
So what does that someone mean by that?
I don't know. So sorry. There's another question that I had in the quiz. They'll probably mail you about this. Can I ask the other question, sir?
Yeah, tell me.
So this question where there was, we wanted to check whether the given tree was a BFS tree or a DFS tree. In that, was it implicit that one has to be the source? Like I thought if 7 were the source, then the C option could be a DFS tree. And
that's a good point. I did not. I tacitly assumed that that was the thing, but one second, let me.
Yes, sir. I also didn't assume that one is a starting node. I thought, I mean, I agree with Aditi, what she said.
Yeah, that's a valid point, but
Yes, so like also like in the first option also becomes right if you assume 7 as the root.
So there are two different options which become correct if you assume that other can be known.
I think A and C become correct. And
But
The order.
we weren't able to choose multiple options, right? So I mean,
yeah. But it's a natural assumption to make, that the root is at 1. I should have said that, but
yes, sir, but it is also natural to question that assumption.
so what are you saying again? 7 is the root, you're saying. 7 is the root, then what becomes, so which one?
Options A and C both become correct.
A and C.
Yeah, I think 4 needs to be the root.
A is not a BFS tree. Is A a BFS tree?
yes, I think so. If we start from 7.
From 7, if we go to 6 and 4, and then we go to 2, and from 4 we go to 3, and from 2 we go to 1, and 3 to 5.
Technically, I mean, it does not have. So you are saying it does not have any back edges, correct? That's what you are saying. It has only cross edges, but that's not a sufficient condition for BFS tree if we want to be sure of that, correct? So can you find an ordering of the vertices of the list such that it is a BFS tree coming down just for technicalities? You see my point?
I think the traversing Aditi mentioned works from 7 to 6 and then 4 to 2 and then 2 to 1 and I mean 4 to 3 and so forth.
7 to 6.
If we just consider this list in a descending order, then the normal BFS algorithm that you had mentioned, that you had written, would work.
Okay.
So we first explore 6 and then 4.
Huh.
So for 6 we get 2, for 4 we get 3, and then 1 and 5.
I see. So what did you mark? I admit that the question is not correct as it's stated, but nevertheless, which one did you choose? Those who were confused between these two?
I chose C, sir, because C also has.
I chose A and I also mailed you about it right after the quiz.
Okay. Let me think about it and I'll get back to you. Correct.
Sir, I think B is valid as well. If we start from 4, I think we can go from.
Yeah. Maybe it's valid. So the point is, I should have specified the root. I should have specified the root. Yeah, that is a mistake. Yeah. Or I should have given the directions of the arrows in this thing. Okay, I will think about it. So whoever has problems, mail me about it. Correct?
Okay, sir.
Okay. Thanks. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.